So this is going to look at a problem of graphing motion, and the problem reads you're traveling west, and we'll call east r positive, for a few minutes at a constant velocity. When you see a red light ahead and begin to slow down to a stop. You slow down at a constant rate until you come to a stop. So we want to draw a position, velocity, and acceleration graph to describe this motion. Okay, so let's just jot down a few of the ideas that we have in terms of the information. So first we said east is positive. Okay, so of course that means west is negative. All right, it tells us that we are traveling west. So we are initially traveling west. So that means we're traveling in the negative direction, which means we have a velocity. If we are moving, we have a velocity in the negative direction. It says that we're traveling at a constant velocity for a few minutes, and then we begin to slow down. So constant for a few minutes, and then we slow down, which means we decrease our value, our magnitude of the velocity. We're getting slower and slower and slower until we stop. And that means we're going to reach a velocity equal to 0 meters per second. So we want to think about how that looks. And I think when we have motion information, it's easiest to start with the velocity graph. So let's do that. So it says we're traveling west, which means our velocity is negative. Now it doesn't give us a value. That's okay. We're just going to define some value. So let's say this is our initial velocity. It's negative because we're traveling west, so it's going to be below the axis. And it says we're traveling for a constant velocity for a few minutes. So the velocity value is not changing as time goes on. So if I move a little bit further in time, I have the same value. So a constant velocity on a velocity versus time graph is given as a horizontal line at the value of the velocity we're going. Negative to the west at a constant rate. So we'll say that represents a few minutes. We then slow down, which means our velocity value is getting less and less and less. And we slow down at a constant rate according to the problem. That means a constant rate means a straight line on the graph, a sloped straight line, a constant rate. And so if our values are getting smaller and smaller and smaller at a constant rate, then they are moving towards the 0 value, which is no velocity, slowing down at that constant rate until we stop. And then our velocity is equal to 0. So this is how our velocity versus time graph looks. And then we can move into the other two graphs by thinking about how is velocity versus time related to acceleration, and then of course back related to position. All right, so acceleration versus time graph. Well, if the velocity is constant, that tells us that it's not changing. And if it's not changing, well, then there's no acceleration. Our acceleration value is 0. So that's a conceptual way to think about it. The other way to think about it is, well, the velocity graph gives us the acceleration graph if we look at the slope. Remember, acceleration is the derivative of velocity, the change in velocity per time. So the slope of the velocity graph gives us the acceleration. The slope of this horizontal line is indeed 0. So both conceptually and that mathematical approach. All right, then it tells us we slow down at a steady rate. Steady means the acceleration is constant. So representing constant on a graph, we know it's a horizontal line. Slowing down doesn't tell us if it's positive or negative, remember. It tells us the change in velocity. So if the velocity is moving in the leftward direction and slowing down, the acceleration has to be opposite that motion. Opposite of left, or opposite of negative, is positive. So from a conceptual standpoint, the acceleration is a positive constant rate, positive value. From a mathematical perspective, the slope of the velocity graph gives us the acceleration graph, and this slope is a positive constant slope. And so it's consistent with our conceptual description. All right, and then we have, so that's about the same amount of time. Then we have the velocity hitting that 0 value and staying there, so it's no longer accelerating. And we have a constant acceleration of 0 value. So that's our acceleration graph. Now, we're not going to worry about these transitions in sort of the real world. We're going to be, speeding up to that constant rate and slowing down. We're not going to worry about those transitions at this time, okay? All right, as we go in the other direction from velocity to acceleration, we know mathematically it's the integration of velocity gives us the position. And so our position graph needs to reflect the slope that the velocity graph describes. All right, so we are moving at a steady rate in the west, the negative direction. So our position is changing. We are moving. And we're moving in the negative direction. Now, knowing velocity information and given what we've been told, we don't have any information about where we are located. Remember, we have to define an origin. So let's do that. Let's say that the stoplight is the origin. We have to define an origin whenever we talk about position because that's where the zero value is. And we don't really know where we are relative to that zero value unless we define the zero value. So I'm going to say that the stoplight is my position x equals to 0. So if I'm heading west, negative, towards the stoplight, I'm heading towards this 0 line. That means I could either be going like this or I could be going like this, towards it. Well, if I'm heading in the westward direction, the negative direction, I have to be heading from a more positive value to a less positive value on the top of the graph. So leftward direction. So I'm going to start somewhere up here. It tells me that I am heading towards that at a constant rate. Well, that means that my position, is changing at a steady rate, has a constant slope. Or the integration of a horizontal line is a straight line, a straight slope. It's negative, so that slope has a negative slope associated with it. And that's consistent with the conceptual description. It then says I slow down until I come to a stop. And we come to a stop at that stoplight. Well, slowing down is represented by changing my position less and less and less and less as I move through time. The slope of that graph gets shallower and shallower and shallower as represented, the slope of this graph, at a constant rate. The slope gets less and less and less. And so my position graph takes on a curved quadratic function when we look at the math of that as we come to a stop at the stoplight. That transition could have been a little bit better. There we go. Whoop. And if we're at the stoplight, we're going to hit the actual 0 point at the point we come to a stop. So we need to define where our position 0 is on our position time graph explicitly to know where we start relative to that position 0. Now, this isn't the only graph you could have done if you set your origin at a different location, but the shape of the graph is what's important here. All right, good job.